As requested, this video is on particles and antiparticles. In 1950s and 60s, the physicists were busy smashing different things together and creating different kinds of particles. This is an animation of the particle collider at CERN, Switzerland. They called it a particle zoo because many kinds of particles were being discovered. So we're going to start first with something as simple as particles and antiparticles. So it has been discovered that every particle, whether it is an electron moving around the nucleus or a proton or a neutron, has an antiparticle. So antiparticle is nothing but a particle that has same mass but opposite charge, electric and magnetic properties. Okay, so opposite electric charge and magnetic properties. For example, electron is negative charge, so its antiparticle would have exactly same mass as electron, but its charge would be positive, so would be denoted as E plus. So E plus would be antiparticle of electron, which is also known as positron. Now, neutron will have exactly same mass as that of neutron, but the charge would be 0 because neutron has no charge. A proton would have a antiparticle of, so if I'm denoting proton by P, so just making it P with a positive charge, its antiparticle would have a negative charge, but the mass would be exactly same. A neutron mass would be exactly same and the charge would be 0. So antiparticles, subatomic particles, same mass but opposite electric and magnetic properties. So go ahead, pause and go through every single antiparticle of electron, proton, neutron and neutrino. Neutrino is energy particle, charge 0, there's no charge, and there is no charge of antineutrino too. Do you know that about trillions and trillions of neutrinos pass through human body every second and we can never feel them? This is because they never interact with our body. Anyways, so next thing, now why do the different particles behave differently, or what is the basis of classification of different particles? For that, let's just revisit this concept. The entire, in our universe, in our known universe, all the forces that act on different bodies, they can be divided into 4 categories: weak, electromagnetic, strong force and the gravity force. So I'm just writing here. So the 4 forces are weak forces. These are generally inside of the nuclear particles like protons and neutrons. Strong nuclear force is a very strong force that is inside the nuclear particles, between the nuclear particles. This is the one force which is keeping the nucleus of most of the atoms intact. Third is the electromagnetic force. The most common example of this force would be the force between 2 magnets which repel or attract. So that is an example of electromagnetic force. The force of friction between your feet and ground is electromagnetic force. The 4th force is the gravity. Okay, this is a force because of which we are bound to earth. So basis of the classification of the particles are these 4 fundamental forces, and on the basis of these 4 fundamental forces, the particles are then characterized as different. Let me just show you. So I've made this diagram earlier. So every single particle, again we're talking only about the subatomic particles, they can be categorized into first 2. So this is first is leptons and then hadrons. So 2 leptons and hadrons, and then hadrons can be further classified as mesons and baryons. Leptons are the fundamental particles. What does that mean is they cannot be further broken down into other subatomic particles till date. So examples are electrons, muons, and neutrinos. So these are fundamental particles. They are an example of leptons. Hadrons are not fundamental because they can be further broken down. They are said to be made up of something called as quarks. So hadrons are not fundamental. Leptons are fundamental. The hadrons are two different categories depending on how many quarks and what type of quarks do they have. I'm going to talk about it in a minute. So hadrons are mesons and baryons. Example of mesons is pions and kaons, and baryons are protons and neutrons. They are, because they're different names, it is difficult to remember. I know, even when I meet a new class of 30 students, the different names, they sound exactly to me like these names are sounding to you right now. So it's okay if we see them often. If I see my students often, I know them, I remember their name. So once you know these leptons and hadrons and mesons and baryons, you will remember their names. So let's get going. Let's first start with hadrons. So I've just written this, pause, and you can go through it. So to understand hadrons, let's just first understand what are quarks. So quarks, they are the most fundamental particles. They cannot be further broken down. They have fractional electric charge, and they are the building blocks of matter. So they make up hadrons, such as protons and neutrons. So if you see inside the nucleus you have protons and neutrons, and what are protons and neutrons made up of? So if I just make okay, that's a horrible circle. So if I just erase it, okay, so if I make an atom, and inside the atom you have protons and neutrons. So if I see what is a proton made up of, so proton is made up of quarks. We have not yet discovered that can quark be further broken down. So far quarks are the fundamental blocks of matters who make up protons and neutrons, and so they are makeups of protons and neutrons. And so we know that quarks are basically kind of three types. So we call it three flavors: an up quark, a down quark, and a strange quark. And just like any other subatomic particle, quarks also have their anti-quarks. Say the anti-quark of up would be anti-up. Okay, and the down would be anti-down. And then the strange would be anti-strange. So we have a combination of 6 quarks to form protons and neutrons. Now, how are actually protons and neutrons made up of the quarks? Let's just see that. First, this. So I made this table earlier, so to save on you some time. So flavors and up. So the black are quarks, and the red one is anti-up. So U is up, anti-up, down, anti-down, and then strange and anti-strange. The charge on up quark is +2/3e, so it's a fractional charge. Quarks have fractional charge. Okay, they do not have integer charge, but hadrons, which are made up of quarks, will have integer charge. I'll talk about it in a minute. So go ahead, pause and see what is a baryon number. We'll talk about it in a minute. Just wanted to make the table now. So hadrons. So going back to this picture here, hadrons are made up of quarks, and then what is the combination of quark that would decide whether a given hadron will be a meson or whether it will be a baryon. So let's just talk about hadrons first. So what makes up hadrons? So hadrons are made up of quarks. Okay, so they're made up of quarks, and because they are made up of quarks and the quarks have charge, and because the quarks have charge, they interact with each other because of a strong force, strong electromagnetic force. And if we try to see what individual quark has fractional charge, but when they combine to give the total charge to a hadron will always carry a net integer electric charge. So the charge on a quark is fractional, but the charge on a hadron is always an integer. Okay, for example, we know that there are two types of hadrons. Okay, so the two types of hadrons are baryons and mesons. So baryons, it is made up of three flavored quarks. So S, D, U, strange, down or up quark, whereas mesons are always made up of a quark and its anti-quark. Example, pions and kaons. Okay, let's just see some examples. I'm just going to show some examples. So let's say, what is the combination of quarks in a proton? So let's just do that. Just give me a second. All right, there is some problem. Okay, so proton is, what is the total charge of a proton? The total charge of a proton is positive. So it is made up of two up quarks. So one up quark is 2/3 e, so 2/3 and one down quark. So if I'm just writing here, so a proton is then made up of 2/3 e plus 2/3 e is a unit of charge, and one, say, two up quarks and one down quark. So this forms, what's the total charge then? So if you see 2/3, 2/3 is 4/3 minus 1/3 is 3/3, so that is 1e. So the charge of a proton is 1 e, that is the charge of proton is equal to that of an electron, but it's only positive. But if I see the charge of a neutron, what is a neutron made up of? It is made up of one up quark, that is 2/3 e, and two down quarks, so minus 1/3 and minus 1/3. So if I just write neutron here, so 2/3 e minus 1/3 e minus 1/3 e, which is 0. So one up and two down quarks. So baryons, protons and neutrons, made up of any of the 2 or 3 flavored quarks, but mesons are always made up of one quark and one anti-quarks. All right, so this we need to know that hadrons have an integer charge always. Now the next one is leptons. Now if you go back to that picture, you'll see I told you that leptons are the most fundamental subatomic particles. Okay, they cannot be further broken down. So they are the most fundamental subatomic particles. They do not feel the strong force. They always interact via one of the three forces, either weak forces, electromagnetic forces, or gravitational forces. So, and there are 6 kind of leptons. Again, they do not feel the strong force. They just interact via weak gravitational electromagnetic forces. And I'm going to now just show you what. So here, so they do not feel the strong force. They are interacting always via weak electromagnetic or gravitational forces. And as you can see on your screen, there's 6 types of leptons. So charged leptons, okay, electrons, muons, and tau. So these are charged leptons, okay. These are the one, say, neutrinos are electrically neutral. And then anti-leptons, each lepton has a corresponding antiparticle, and that antiparticle will have an opposite charge, whereas its mass would be identical. So if it's a lepton, its lepton number is +1, whereas if it is an anti-lepton, its lepton number would be -1. Okay, so electron lepton number would be +1, whereas if it is an anti-lepton like positron, its lepton number would be -1. Now let's just do one question here. Go ahead, pause and try to do it yourself. A muon belongs to a family of particles called leptons. Fine. State two features that all particles in the lepton family have in common. Right. One simple thing you can always say, each particle will have an antiparticle, whether it's in a lepton or a hadron. So each lepton has an antiparticle, first number. Leptons are fundamental particles. Okay, we know that they cannot be further broken down. Leptons interact via weak forces, and leptons have always a non-zero lepton number. Okay, so you can just write each lepton particle will have an anti-lepton. Okay, so because it's just saying 2, lepton number is never 0. So okay, or you can just say leptons are fundamental particles, so that would be the third feature. Now, according to the standard model, the pion and muon are classified within 2 different groups of particles. Now, go back to the video if you do not know the answer to this one, which group each particle belongs to, and describe the 2 groups. Okay, so which group does each particle corresponds to is, I am hoping that you already know the answer. Muon is a lepton. Perfect. Muon is a fundamental particle because it's a lepton, and lepton is always a fundamental particle. Pion is a meson, and meson is an example of hadron, and hadrons specifically combination of a quark and an anti-quark. Okay, so just writing here, muon, okay, is a lepton, which is fundamental particle, and then pion is a meson. So pion is a meson, which is made up of a quark and its antiquark, always. Okay, next. Muon are examples of leptons, fine, where pions are example of mesons. A structural difference between lepton and mesons. Leptons are what? Leptons are fundamental particles, whereas mesons are just made up of quarks. That's it. That's a structural difference. Leptons cannot be further broken down, whereas mesons are made up of quarks. Just the previous question. Okay? It is just familiarizing ourselves with these names over and over. So more you meet the new people, more you know them, more you remember the names. Okay, let's do this one. What is the number of down quarks and the number of up quarks in a nucleus of this atom? It's a fluorine atom. Now, let's see. The nucleus, I'm just drawing the nucleus. It has 9 protons and it has 10 neutrons. 19 minus 9 is the number of neutrons. Now, protons is made up of 2 up and 1 down, and a neutron is made up of 1 up and 2 down. times 10, and this is times 9. So total up quarks are how many? 9 to the 18 plus 10, 28. And what are the total down quarks? Down quark is 9 down quarks and 10 to the 20, 29. So that's my answer. Okay, total down quarks and total up quarks. A sigma particle is a baryon. Okay, it can decay into a positive pion and a neutron. So this is the quark. The sigma particle has one strange quark within its structure. Now it's decaying into a pion and a neutron. Okay, we should not have done this question now, but it's okay. Now, what is it? It has to have a one strange quark in it, and because the one strange quark is -1/3,